We have previously discussed in class that the determination of the strength of an acid is how much it dissociates or breaks down into ions when it's in water. So the stronger an acid is, the more completely it breaks into ions. In fact, the definition of a strong acid is that it dissociates 100%. There's no acid that's intact, it's all broken into two ions. On the other hand, the weaker that an acid is, the less that it dissociates into ions when it's placed in water. So determining the pH for weak acids and bases, you can't just take the concentration of the acid and say that that is the concentration of the hydrogen ion, because not all of the acid dissociates. So we're going to have to do an extra step, consider a little bit more what's happening when we're dealing with an acid that's weak. Also, when we're dealing with an acid that's weak, we're dealing with equilibrium rather than a reaction that goes to completion. And so we'll always have to have an equilibrium constant associated with that. And for acids, we call that Ka. For bases, we call it Kb. This is a monoprotic acid. We haven't talked about that a lot, but you can probably break it down and figure out monoprotic means one proton. And if we're just talking about a generic acid, you'll see this a lot. We usually represent a generic acid as just HA. So A would be whatever the base of that acid is. It could be Cl, it could be a whole lot, it could be CN, it could be a lot of different things, but A just means a generic acid, and the H represents that one proton that's available to donate. So when you put a weak acid into water, you get an equilibrium. Again, that double arrow is associated with the fact that this is weak. It does not all dissociate. So HA is aqueous, water is liquid. Because it's an acid, it's going to donate that hydrogen to the water. The water becomes H3O plus, and we're left with the conjugate base of that acid, which we'll just generically call A minus. And we're going to bring back in ice tables, which we learned for the first time in the fall, because this is an equilibrium situation. What we know here is that the original concentration of the acid was 0.122 molar. And in an ice table, unlike a BCA table, an ice table is for equilibrium, so we're going to use things that have units of molarity in the ice table. We're not going to worry at all about the concentration of the water, because it's a liquid and that doesn't affect equilibrium, so we can just kind of ignore that column. We're going to assume that at the beginning there's no hydronium. Now that is an assumption. There is some hydronium in the water that's present, that's already there from the autoionization of water. But we are going to make an assumption when we're putting an acid into water, the acid is going to contribute so much more hydronium, that the amount of hydronium that was already present from the autoionization of the water is negligible. So maybe you want to make a note that we are making that assumption. So when the acid goes into water, it's going to dissociate. That's what's going to happen in the change line. So this would be minus X plus X plus X. So the equilibrium concentrations would be 0.122 minus X, X, and X. The next thing we need is we need a Ka expression. So for, again, keeping in mind you only include things that are aqueous, so the Ka expression is hydronium concentration times the conjugate base concentration divided by the original acid concentration. So products over reactants, and all the exponents are 1, so that makes that a little easier. Plug in what we know. The value of Ka was given to us as 5.7 times 10 to the negative 4th. The hydronium and conjugate base are both X, so that gives us X squared. And the equilibrium concentration of the original acid will be 0.122 molar divided by, or minus X. We need to solve for X. We have a shortcut that we learned back in the fall that if we assume that this x is small in comparison to 0.122, we can neglect that. So we'll try that shortcut first, because that would make our lives a lot easier. So if we do that, I get x is 0.0083 molar. This shortcut only works if we have if x is less than 5%. So I'm going to check that. 0.0083 divided by 0.122. And unfortunately, we get 6.8%. So our assumption is not okay here. We cannot neglect x in this case. So that doesn't work. That means we have to, in this case, go to the quadratic formula. So I'm going to take this and I'm going to rearrange it so that I have a quadratic that's set equal to 0. So I got 6.954 times 10 to the negative 5th minus 5.7 times 10 to the negative 4th times x minus x squared equals 0. And I just used the quadratic formula. You can program that on your calculator, or we talked about how to use the calculators in my room to do that. And I got x equals 0.0081 molar. Now, usually a problem doesn't stop here. It doesn't just require you to figure out x. You're going to think about, okay, what does x mean? A lot of times it will say, okay, what are the equilibrium concentrations of all the species that are present? Well, we go back to thinking, what did we just do? We figured out how much of this weak acid became ions and how much still stayed intact as HA, as the undissociated acid. So HA at equilibrium is 0.122 minus x, which will be 0.114 molar. And the concentration of hydronium is equal to the concentration of A minus at equilibrium, because they're both going to be x based on our BCA table. And their concentration will be 0.0081 molar. Now, something that a lot of students forget, there is one more species that is present in this situation. It doesn't show up in this chemical equation that I wrote, but it is there and it still matters. Anytime we're talking about acids and bases, there are always two species that we can figure out the concentration of. Hydronium, and we've got that here, but hydroxide is there as well. So if you are asked to figure out the concentration of all species at equilibrium, you cannot forget hydronium or hydroxide. They both need to be there when we're talking about an acid and a base. Well, how are we going to figure out the hydroxide concentration? I'm going to have to move to the next page, but if you think about it, you do know how. We know that Kw is always the hydronium concentration times the hydroxide concentration. So if we know Kw, which we do, and we know the hydronium concentration, you can figure out the hydroxide concentration. So I'm going to do that on the next slide. So Kw is 1 times 10 to the negative 14th. I don't know the hydroxide concentration, but I did figure out, or we just figured out, that the hydronium concentration is 0.0081. So if I divide both sides by 0.0081, I can figure out the hydroxide concentration. And I figured out that the hydroxide concentration was 1.2 times 10 to the negative 12th molar. It's also worth keeping in mind, this is an acid. So it should make sense that the hydronium concentration is much, much higher than the hydroxide concentration. We talked about the equilibrium. If the hydronium goes up, the hydroxide has to go down to maintain their product being 1 times 10 to the negative 14th. Now, if you go back to what we are actually asked to do in this problem, I kind of expanded, showed you some other things you could be asked. This problem actually asked, what is the pH? But we can use some more things that we learned in our last lesson. pH is always negative log of the hydronium concentration. So pH is negative log of 0.0081, which in this case is 2.09. Again, if I do a little mental check of myself, this was an acid that I just added in. Even though it was weak, it's still an acid, so I'm expecting a pH that's on the lower end of things, and it is. Also, if you just go back to the original, or the hydronium concentration, and think about putting this in scientific notation, it'd be around 10 to the negative second or third, and that is consistent with my answer. We're going to look at a second example. In the first example, we were given Ka and used that to figure out the pH of the acid. This one's going to be kind of the reverse. We're given the pH of the acid, and we want to figure out the equilibrium constant. This is something that can be done in a lab, and in fact, later this chapter, we will be doing it, so you may want to refer back to this example problem at that time. I forgot to write it down originally, but we are also given the concentration of the acid that was that the pH was measured for. So because this is a weak acid, I'm going to just start by thinking about that equilibrium that happens when the weak acid goes into water. So if we've got HA, now notice I'm going to represent the equilibrium slightly differently this time. The first time I used water and hydronium. This time I'm not going to use water, and so the product will be the hydrogen ion. Both this generic equation and the way that I wrote the generic equation in the first example, both are acceptable. It needs to be understood when you write it this way that really there is water present. So it's, but it can be understood. It can be written either way. So if we did an ice table, we are given that the original concentration of acid that was prepared was 0.060 molar. And we're again going to make that assumption that if we're adding an acid, the amount of hydronium that's initially there from the autoionization of water is negligible. Now, this is interesting. We could do minus x plus x plus x, like we kind of got used to doing in the equilibrium chapter. But we got an issue if we tried to do this, because if we write the Ka expression like so, we don't know the Ka, and we only know these in terms of x. So that's not going to work this time. But we've got one other piece of information that we haven't used yet. We've got the pH. And remember, the pH is really just a lazy man's way of saying the concentration of hydronium that's present. So we're going to use the pH to figure out the hydronium concentration. So the hydronium concentration is equal to 10 to the negative 3, the antilog of the pH. So the hydronium concentration is 0.000363 moles. So we know that at equilibrium, which is what you would have, what the system would have reached when you were measuring pH, the equilibrium concentration of hydronium is 0.000363. So this must be 0.000363. And since these two have the same coefficient and we started with none, this must also be the same value or the same concentration. And we must have, and since these are all 1-to-1 ratios, this change line must be minus 0.000363. And if I do the subtraction, that makes the equilibrium concentration of the non-dissociated acid 0.0596. Now we have some information that will allow us to calculate the Ka, because I know I use the pH and my ice table and my coefficient relationships to figure out the equilibrium constant or concentrations of all the species present. So Ka is 0.000363 squared divided by 0.0596. So the value of the equilibrium constant for this acid will be 2.2 times 10 to the negative 6th. So for a weak acid or base, you can use the Ka to figure out the pH of that acid when it's put into water, or you can use the pH and work backwards to figure out the Ka. The next thing we'll have to look at is how to do similar calculations for bases.